Many engineering teams operate under the assumption that migrating away from classical encryption is a problem for the distant future. The logic suggests that until quantum computers hit commercial scale, current cryptographic standards remain viable. That logic creates monolithic security architectures that shatter the moment hardware capabilities take a sudden nonlinear leap forward. In cryptographic circles, that leap is known as Q-Day. This is the impending horizon event when a fault-tolerant quantum computer becomes a reality. When that machine powers up, data secured by legacy cryptographic primitives degrades into readable plaintext. Robust systems engineering requires actively dismantling these legacy trust models and replacing them with architectures built for post-quantum agility. Postponing this transition until hardware is commercially available ignores the fact that architectures being deployed today will likely remain in service well past the Q-Day horizon. The immediate urgency of this shift is driven by a specific adversarial strategy: harvest now, decrypt later. Right now, adversaries are actively intercepting and collecting massive volumes of encrypted classical network traffic. This intercepted ciphertext is not being discarded. It is being stockpiled in persistent data centers. These actors are simply waiting for Q-Day to retroactively apply quantum decryption techniques to this historical cache. Data has a strict mathematical lifespan. If a dataset requires 10 years of confidentiality and Q-Day arrives in 5, that information is already at risk. Standard transport layer protocols currently routing traffic across the internet offer no protection against this specific latency attack. The threat of asynchronous decryption renders any static, classical data transmission architecture obsolete today. Modern enterprise security rests almost entirely on two algorithms: RSA and elliptic curve cryptography, or ECC. RSA functions because of a specific mathematical hardness assumption: prime factorization. This chart shows the exponential scaling of computation time required to find the prime factors of increasingly massive numbers. A public key is generated by multiplying two primes, and the original factors are kept hidden as the private key. For a classical computation engine, working backwards from a massive public key to isolate those two specific prime factors takes an exponential amount of time. But look at what happens to this graph when we introduce quantum processing. The curve drastically flattens out, reducing the required calculation time to a mere fraction of what a classical processor needs. Classical security relies on a temporary gap in computational power rather than an absolute mathematical barrier. The specific mathematical stressor that breaks this assumption is Shor's algorithm. Shor's algorithm reframes factorization into a problem of finding the repeating period, or periodicity, of a function. This diagram demonstrates how a quantum circuit handles that periodicity. By feeding phase estimation data into a quantum Fourier transform, it collapses a highly complex wave pattern into a single frequency spike. A classical machine must evaluate and guess potential factors sequentially, one after another. Quantum superposition bypasses that bottleneck, evaluating all possible periodicities simultaneously across the entire function. The algorithm then uses quantum interference to cancel out incorrect probabilities while amplifying the correct repeating period. This means a problem requiring exponential computational time mathematically collapses into a problem solvable in polynomial time. Against this shortcut, legacy primitives like RSA and ECC offer no structural resistance. Shor's algorithm transforms the algebraic foundation of classical encryption into a mathematical liability. To survive this vulnerability, systems must transition away from prime factorization and adopt lattice-based cryptography. A mathematical lattice is a highly structured grid of intersecting points, but cryptographic lattices do not exist on a flat plane. This geometry extends into hundreds or thousands of spatial dimensions. This structure introduces a different hardness assumption: the shortest vector problem, or SVP. The objective is to start at an origin point and navigate through this multidimensional complexity to find the specific lattice node that is closest to zero. Calculating the exact distance between nodes across 1,000 different dimensions requires an extraordinary expenditure of computational power. Crucially, unlike the periodicity trick utilized in Shor's algorithm, applying quantum superposition to the shortest vector problem offers no exponential speedup. By shifting the defensive strategy from algebraic factorization to geometric complexity, lattice-based cryptography provides a structure that can survive a direct quantum stress test. Understanding lattice mathematics is the first step, but the second is engineering the practical implementation within a system. A common engineering error in legacy systems is hard-coding specific encryption algorithms directly into the application layer. This diagram shows an application, API, and cryptography layer rigidly locked together. When cryptography is tightly coupled, compromising the underlying algorithm breaks the entire system above it. Escaping this fragility requires adopting a standard known as post-quantum agility. Cryptographic agility separates the cryptographic primitives from the core application logic by inserting an abstraction layer. This abstraction layer functions as a universal translator, handling secure data routing regardless of which specific mathematical primitive sits beneath it. With this decoupled framework, the system achieves dynamic updatability. A compromised legacy module can be removed and replaced with a lattice-based primitive without rewriting the top-level application code. This modularity allows engineering teams to swap cryptographic protocols while maintaining system uptime. Post-quantum agility assumes that cryptographic evolution is continuous and builds an architecture ready to absorb new mathematical breakthroughs. Software systems must complete the transition from relying on static algebraic trust to operating within dynamic, modular frameworks. The exact calendar date for the arrival of fault-tolerant quantum computing remains uncertain, but the necessity for architectural preparedness is a present-day requirement. Legacy maintainers will react to the breach. Proactive architects are designing systems today that anticipate the collapse of current encryption standards. Attempting to retroactively patch a tightly coupled, hard-coded system after a quantum-level compromise is a failing strategy. Mastering lattice-based implementations and achieving post-quantum agility is the definitive benchmark of modern, resilient systems.